Hello community! Today we are on Mars and we do a little update of our Mars rover. So what is it? Now imagine we are on Mars and there's a little box waiting for you. And not to go with any confident experiment, let's say we have to buy a shelter for the first human astronauts on Mars. So how we do this? Well, we have some instruction in the box how to assemble this with our robotics system. So you look at this, it's okay, that looks interesting. And I say, oh gee, now we need some precision robotics assembly instruction. How do we do this with artificial intelligence? Now let me be clear, we are not talking about this in a controlled environment where everything is absolutely positioned with a precision on a millimeter, sub-millimeter base. Every robot knows exactly I have to go 3.6 millimeters to the left and then 8.9 millimeters upwards. No, we are in an uncontrolled environment. And you might say, okay, so I have to provide my rover now with a new intelligence. So you showed us here just 2 days ago, I said, hey community, you can here, and NVIDIA did this here, create new LLMs by pruning here bigger models like NVIDIA's Nemotron. Is this the way forward? And if you look at the literature here by NVIDIA, mid of July 2024, how they can build compact, smaller language model via pruning here after a huge model, you see this helps only NVIDIA to produce it cheaper. Because here on the x-axis you have the cost for NVIDIA to produce those models, and you see with pruning you just make it cheaper for NVIDIA. But the level is about here a Gamma 7B, a Minitron 8B. You see the performance is more or less the same, it's just cheaper, so this is not the solution. So the solution is of course behavioral cloning with AI. So what is the idea? We have on Earth a supercomputer center, huge vision language models here, and we have to find a way to transport this AI intelligence to our rover on Mars. And this is an edge device with a tiny computer and just a little bit of energy. So what is the best way to do this? Now, if you're an expert, you know behavioral cloning currently stands as the dominant paradigm for learning real-world visual manipulation. So let's go with this. Now, behavior cloning, is here a sub-function of imitation learning. And imitation learning, we know for years, it's powerful machine learning techniques where an AI agent learns to perform a task by observing an expert, a human expert, a machine learning expert, performing that particular task. Now, the features here of imitation learning is simple. You have an AI agent trained using now the data set of those expert demonstration, learning exactly how the task should be performed, how we built here the shelter for the first human astronauts on Mars. And these demonstrations can be in the form of trajectories. And what are they? They are sequences of actions and observation, where you can even have a static data set of the desired outcomes. So please note, unlike reinforcement learning, where the agent receives a reward from the environment for its action, imitation learning is now something different. Imitation learning learns directly from the expert behavior, and only the expert behavior. There's no feedback from the environment. And this makes it less demanding in terms of defining here complex reward function on Mars, which can be challenging in complex environments, and our little rover has just a little bit of energy. Now you know that behavioral cloning is now the simplest and most straightforward approach to imitation learning. So primary category imitation learning, subcategory behavior cloning. And we have here that it directly learns a mapping from the states to the actions simply by imitating the expert actions. So it does not understand or develop with trial and error, but it just learns the expert actions. That's it. Simple. So what what we have to send to our rover on Mars. We have to gather a data set of state action pairs from the expert demonstration here on Earth. So those are, if you want, our training data. And then we train here a policy function on a neural network now that maps the states to the actions using now the collected expert data from step 1. And this policy learns now to predict the action the expert would take in each state. So we are not exploring here the action space in its entirety. We have a clear path forward, laser focused. And then this trained policy is used by the agent on Mars to perform the task. Imitation learning. Beautiful. For my green grasshoppers, what is a state, what is an action, and what is a policy in this content here, just to be here in a complete definition frame. Now, if you want to enter this, I learned here from this publication, MIT, October 2023, Generative Behavior Cloning. And I think this is an excellent paper to enter this area. Then, of course, you see here, June 2024, University of Washington, and they were looking here for, where is it? To generate corrective labels. And they were looking here for a local Lipschitz continuity. But as you see, they discovered that in general, we need some corrective measures for the fine-tuning of the imitation learning. And this goes here, if you remember Google Brain Robotics here, beginning of 2023, they used here for their imitation learning Taylor series. And they here had a methodology where they also looked at the deviation in the higher order Taylor series terms between the learned policies and the expert policy. So you see, it developed over years, and today we look at this. End of July 2024, MIT, Harvard, Residual Reinforcement Learning for Precise Visual Assembly. And yes, we are talking here about reinforcement learning in the fine-tuning phase. So what we are talking about? We are talking about reinforcement learning-based fine-tuning in advanced robotics. You know, I explain what is this here in this video here. But of course, we go a step further. We talk about residual reinforcement learning-based fine-tuning. And since we're operating on Mars, we will utilize here a behavior cloning methodology from MIT. So here you have it. This is what we are focusing now in AI, how to code this. But at first we have to understand what is going on and why MIT chooses this particular methodology for robotics. Now, as you can see here, this is the state of the art. If you just have 40 real demonstration for your robotics and you have a non-controlled environment. The objects are not on a grid. They're somewhere on the table. You see, this is our state of the art. Now, if we add 350 computer simulations to this, you see, with more data in the learning data set, look at the precision. Now it increased significantly. And as you can see, we have on the arm a camera to make here some close images. And look at how precisely now this system is able to do it. And this robot was learned this behavior here, exactly here with what we are focusing today. Now let me show you in detail. We have to address the complexity of learning from a high-dimensional visual data in robotic manipulation, and we do this with this new framework by Harvard and MIT, which improves the robustness of the policy by allowing them, and now the interesting part, to learn corrective actions on top of a frozen behavior cloning methodology through, you notice, task rewards and exploration. So we are not opening up the complete action space, but we say we have from our behavioral cloning the main path through this action space. And now with this RESIP new framework, we allow now corrective small little action. And we see or we analyze which action are successful for our task. Here from the official paper, simple process, 5-step. You collect here the simulation demonstrations. You have your base policy. Then you improve your policy if you run here, 400 computer simulation to update here the residual policy on a frozen BC base. Then you generate expert trajectory now on this additional data. You render now realistic and diverse dataset in synthetic computer environments, CAD environments. Plus, you collect now for your particular task to build a habitat on Mars, some real-world demos from Earth, and then you co-train everything together. So you have your real data sets. Let's say you only have 10 or 15 data sets from the real world, but you have hundreds or thousands of synthetic data sets. You combine them, you train them, and you have your final real-world policy. Now, if this is a little bit too complicated, never mind, we do it again. So we have per time step residual policies that were trained with our classical OpenAI PPO, reinforcement learning, to locally correct now some action chunks predicted by a behavior cloning trained diffusion policy. And you know about diffusion policy, I showed this in detail in my last video. And now we have this BC trained diffusion policy, and we have two phases you already see in the literature. And the first is called the base model, and phase B is called the residual model. Now, base model is simple with the diffusion policy. It predicts the action chunks that was trained via the behavioral cloning that I showed you at the beginning of this video. And now, to increase here the accuracy in our robotic movement, now comes the residual model on top of our BC. And this now makes per time step corrections, little tiny corrections that were trained with reinforcement learning. So what we have a very intelligent approach that does not modify the base model, but combines now the behavioral cloning from our imitation learning and a residual reinforcement learning phase, which allows now for this flexible, tiny optimization that you really succeed in your downstream task. So this phase A and phase B model you also find in the literature. Here you see it in action. Look, the blue line is the residual correction. Normally the red line would be it and we would fail, but with the addition of the blue line from the residual-based fine-tuning in action, you see now that the green line is now the resulting net action that our robotic system performs, and we can place the screw perfectly where it belongs. This is the beauty here. So you have the red line for the BC and you have the blue line for the residual model, and the green line gives you now the optimized residual reinforcement learning based fine-tuning for advanced robotics with a frozen BC. Beautiful. This is it in action. Great. Now, if you want to do further research, there's one open question. Let's have a look at this. And you see here you have the reinforcement learned trained teacher model, the complex model, and we have close to 100% accuracy. Beautiful. Now, you know this is a state-based model, and this we have here on Earth. And then we have here the success rate if we have here the training only on some 5-10 human demonstration. This is not enough for a training data set, so we need to generate synthetic data sets from CAD systems, from computer simulation, whatever you want. This is not a technological problem anymore. And then you have here the red line. And the red line is now the distilled student policy. And you see, we start here, of course, we begin here from the human demonstration, and the number of demonstration we have here, also from synthetic demonstration, the performance goes up, and the performance goes up, but it plateaus out at about 77%. Now, this is interesting. Why is there a gap? Why does the student do not reach here the performance of the teacher? Well, at first you might think, hey, wait a minute. We have a change in the modality because the reinforcement learned or the trained teacher model is a state-based model, like I showed you at the very beginning of the video. And now the student is now our little rover on Mars that only has 1 or 2 cameras to guide the robotic arm to the correct position. So we have now between the teacher and the student a change in the modality, because now our student on Mars is only image-based. And you said, maybe this would explain here the gap here. But they, Harvard, MIT show this is not the primary cause. So if you want to do some research, there's some open question waiting for you. But in general, what we can say now with this latest publication here for computer-guided assembly, robotics, AI-based, we have now that MIT and Harvard propose here training residual policies on top of frozen behavior cloning trained diffusion models using standard policy gradient methods and sparse rewards. I'll show you this in a second. An approach they call now RESIP, stands for Residual for Precise Computer Manipulation Robotics AI. Great. Again, oil-based fine-tuning you find here. So there you have it. The idea is simple. We use now our behavior cloning algorithms for the AI model, for the teacher-student model. One is on Earth, one is on Mars. Plus, we have those residual corrective actions by reinforcement learning-based fine-tuning. So you see, if you want this here, this behavioral cloning here, this is our pre-training now. And now the fine-tuning phase is reinforcement learning-based, which is not anymore the third option of the alignment of the model. So you see, pre-training is now BC and fine-tuning is now RL. And this is it. Now, if you are still watching this video, let's go a little bit more into technical details. What are the core methodological innovation by RESIP? It enhances here the methodology robustness. So what we have an overlay of a residual policy trained via policy gradient methods and sparse rewards on a frozen BC trained model. So this provides us now with small corrective adjustments to the initial policy outputs, which enhances the precision without modification to the BC model. And this is great because we do not introduce now instabilities into the model by directly doing a RL-based fine-tuning of the complete system, but we just adjust here our RL. Now, sparse rewards, what is it? In reinforcement learning, sparse rewards refer to a reward structure where the feedback, the feedback from the environment, which is the reward, is given now not at frequent terms but infrequently. So instead of receiving the rewards at every action or every state transaction that happens, the AI agent now receives the rewards only at specified milestone or upon completion of the task. So this helps us with the computational complexity, and it is also a little bit faster. Another innovation is here that you have the decoupling of the training of the residual policy from the primary BC training. And this separation, if you do the experiments, enhances the stability and the training flexibility. And in the last one, we have here this distillation into a different modality, a distillation into a vision-based policy, because our rover on Mars only has some cameras and nothing else. So the vision-based policy then is also fine-tuned using here a blend of synthetic and real-world data, ensuring now its effectiveness and robustness of the methodology on Mars. Now, I have for myself here always tried to structure this approach. What is the most important fact? So this is not the official literature. This is just my simple thinking. So it all starts, if you want to analyze here this approach by MIT and Harvard, here with a BC training. And here we have our BC allows the robot to quickly learn here a baseline behavior from, let's say, simple human demonstration, providing here a foundation for further refinement. Because reinforcement learning typically requires a more structured learning environment to begin effectively. So we can help the system to get in a good starting position. Then, if we see this here as a BC pre-training, we have here now our fine-tuning with reinforcement learning. And this reinforcement learning introduces the ability to adapt and optimize based on the feedback from the environments. These are our rewards, which is now crucial for learning to handle variation and unforeseen situations. And then, yes, of course, and then comes the block of policy training. Now, what is this? I divided in my thinking into a residual policy training and a policy distillation with the swap here, plus a real-world development phase. So let's have a look at this. First one. Now, the residual policy refines here the action proposed here by the frozen BC trained model, making small but crucial corrections, I showed you this in the video, that align with the actual task where the precision is critical. Remember, the robot was not able in the first video to grasp here the little bolt or screw or whatever it was. It needed some small correction from the camera, from the visual policy, to really be in a position that it was able to fulfill its task. So, why we do this? Because directly modifying the original BC policy with reinforcement learning, this can lead to instabilities and unintended changes in the behavior of our BC policy model. So this is nice if we can decouple this. Then we have the distillation phase. The distillation, what it does, it simplifies the final policy because we want to send it to Mars. So we can't have an extreme complex data stream. Simplifies the policy, transferring what was learned in a complex reinforcement learning environment into a more streamlined model that operates directly on our rover on simpler inputs like the camera inputs, RGB images. And then, of course, we deploy this, we see it in action now on Mars, and we have to validate and refine here the distilled policy in the real-world condition, and just a little tiny bit of training ensure it performs outside of our controlled environments that we build on Earth. You see, this is my way of trying to grasp here this development. Now, for the data sets, I ask myself, wait a minute, so what data sets do we have in this methodology? Now, we learned, or reading this, I understood, okay, so for the BC pre-training phase, it is good to have as a starting point some, let's say, 50 human demonstration to train here a base BC policy. So we have here human guiding here the robot arm to exactly do what the system should do on Mars, build the habitat for the human on Mars. Beautiful. BC policy learns to replicate the demonstrated behavior, but may lack the ability to handle small little deviation. And here's now where our CAD simulated models come in to create here a simulated environment. We generate hundreds of synthetic trajectories, and on those trajectories, 400, 500, 2000, we train a residual policy, our resip, on top here of this frozen BC policy with our classical OpenAI PPO. So you see, this is here the synthetic trajectory data generation. And then, again, we generate here hundreds of trajectory. We create here a large synthetic data set by rendering here the successful trajectories with the visual variation. We bring it all together, and then we co-train the policy using additional maybe real-world demos and all the synthetic data from the reinforcement learning fine-tuning. And then we deploy this co-trained vision policy on Mars. So you see, this is a very interesting approach. You need a lot of synthetic trajectory data, but the way it is built, it is amazing that it is working at all. Yeah, I talked about policy distillation here for my green grasshoppers. It is simply a process used to transfer knowledge from a complex, possible computational expensive policy, this is what we call the teacher policy, to a much simpler, more computational friendly policy known as the student policy. And of course, we have the goal to retain the performance of the teacher policy while simplifying here the execution to an amount to make it suitable for real-time application, robotic systems on Mars that operate only on sensor input like RGB images from their cameras. So, if you want, in the easiest way, policy distillation here is a bridge between sophisticated machine learning models trained in the perfect controlled environment, and it bridges here over to the practical, deployable system that operate in an unpredictable world on Mars where our resources are restrained. This residual policy, it refers to a policy that is trained to correct or to refine the action predicted by another policy. This is our frozen BC policy. So the residual policy, just to remind you, takes the output of the original policy as an input and produces here this correction or this residual action that is so important to be successful in your task on Mars. More for my green grasshoppers if you want to study this in detail. But you also might find here in AI robotics that this two-phase model is further defined. So let's look at phase one and maybe repeat this. So what we have at the very beginning, we have to collect a mid-sized data set of expert demonstration. Each demonstration, each data set consists of a trajectory of the system states and the action by our robotic arm with access to CAD models for additional, more accurate simulation. And then in this behavioral cloning BC pre-training phase, we train here an initial base policy using here the behavioral cloning on the collected simulation dataset. Now the base policy is trained to maximize the likelihood of the demonstrated action given the system states, and we use here a diffusion policy as the base model, predicting multiple future action in chunks to enhance the performance. And if you ask why do we need here a diffusion policy, I explain exactly this reason in my last video. After the pre-training phase, we go now to the fine-tuning phase, which is now a reinforcement learning fine-tuning with Resip. So instead of directly fine-tuning the base policy with the reinforcement learning, we just train a residual policy on top of the frozen BC trained diffusion model. We use here our standard tool set of a policy gradient methods and sparse task rewards. I just showed you what this is to optimize this policy. This residual policy learns now to predict the corrective actions that improve here the overall task success rate, and this is so important. And I showed you here the image of the robot with the red line, the green line, and the blue line. And this approach, MIT, Harvard, residual for precise manipulation, avoids here the complexity of directly altering the base policy with reinforcement learning. So we just operate on an additional top layer with the residual policy. And then Once the residual policy is trained, we use it to generate a large synthetic data set of high quality trajectories. So we generate here all these synthetic RGB images, which will be so important as a data set, as a learning data set then, because we have to employ this policy on Mars. So this large synthetic data set of the high quality trajectories with the residual corrections consists now of RGB images observation and their corresponding action of the robotic arm. And now this is suitable for a vision-based policy distillation. You might find that this is also the content of phase 1. Whatever you like to imagine, however you want to approach this learning phase, whatever helps you, go with what you like. The content, of course, is always the same. Now, phase 2, an alternative representation of the same topic, is then, of course, it helps to collect a small set of real-world task demonstration 5 to 10 to help bridge here the simulation to reality gap that I showed you, 77% to close to 100%. So what we do, we combine now the large synthetic data set from phase 1, now with this small real-world data set demonstration, and this combined data set, which is now even more precise, helps now to adapt the policy even better to the real world now, accounting here for the very minuscule differences in visual appearance and dynamics. So we have another training cycle if you want, and then you train here a final vision-based manipulation policy using here behavior cloning on the combined data set. And this policy now operates directly from RGB images from our visual sensor on Mars, making it now really suitable. This is the best way for real-world deployment on our Mars rover. You deploy this trained vision-based policy on your robotic system, and it should be able now to build the human habitat on Mars. If you want to have the code of all of this, if you want to have a very nice video, this is the page you should go to, residual-assembly at GitHub.io. MIT, Harvard, Improbable AI, and they show you here much more detail if you have a policy input only from the front camera and the wrist camera. You see here this little wrist camera for the detailed images, and they explain here in a beautiful detail much more how this works, where is their data set coming from. And I just want to show you this AI lab, this improbable AI. I was not aware what it is. Well, of course, it is MIT, Computer Science and Artificial Intelligence Laboratory. And over there, they have this alliance here. There is their improbable AI lab. And you have here from the assistant professors of the Department of Electrical Engineering and Computer Science at MIT. He shows you here in 8 minutes a walk around. You get familiar with this AI lab. And here you have videos, and I would recommend this YouTube channel here, MIT Computer Science Alliances, shows you here the work of a PhD students. And he focused, for example, here on the simulation to real robot learning exercises here. So real nice. If you want to learn more about this, I really appreciate if PhD students do a short video and show their laboratory, show their results. If you have here such a beautiful demonstration object, hey, you can be proud of your research. Great. Yeah, code, I told you, GitHub. You have all the Python programs there, whatever you like, it is available there, MIT. Great, go there if you want to have a deep dive. This is the code base I would recommend. Beautiful. And now we are at the end of this video. So we were talking about, if you want, the latest research in AI robotics. We had a simple task to assemble here a human shelter. Maybe you are familiar with this particular visualization, you know what I mean. But of course you might say, so this behavior cloning, this is now the state of the art today. But do we know what will be the future in behavior cloning? And you might ask, of course, we can look at the current limitation in BC and get an idea how we can overcome this current limitation. And you're not going to believe it. Of course, it struggles to generalize to more deviating, unseen situation. If the screw is really displaced on the table, or it is somewhere else on a different surface, or we have completely noisy data or incomplete data stream as an input. For the no error correction of the classical BC, in this video we found a kind of solution with our residual policy optimization. But there's one block that is still causing problems, and this is distribution shift. So if the expert behavior, the main source where our AI agent is learning, copying, imitating, is not representative of all the possible scenarios that our little rover on Mars will encounter, our agent, our rover on Mars, may perform poorly in this real-world situation on Mars if a distribution shift happens in the training data. And now, if you're interested, I think in my next video, I show you what is the current research in this problem area of distribution shift that currently affects here our research in behavioral cloning in AI robotics. Okay, this is it for today. I hope you enjoyed it. I hope you found some new ideas, maybe learned some new facts, and it would be great to see you in my next video.